There are no significant difference, and there is significant difference.
There what? Say what?
Almost could ask if when you have two sets of data, and everyone's asking if it's three.
Homoscedastic means there is no significant difference between the variances.
Yeah, homoscedastic, no significant differences between the variances. In Excel, that's a number 2. Okay. Heteroscedastic, it means that your data are not parametric. You do have a significant difference in the variances. You go to a number 3. Okay. So if your f-test value, your p-value is greater than 0.05 for your f-test, it means you have, we are assuming, it doesn't actually mean it's homoscedastic, we're assuming it's homoscedastic at that point. The paired t-test. We haven't talked much about the paired t-test. What's its purpose?
It's for when the two data sets for the samples are not individual. There's a variable that connects them together.
They are not independent, right? So the data points are connected. And many of you may be using a paired t-test. Paired t-test is wonderful. Okay, so basically here's 3, so basically f-test, does the data have to be parametric? Yes or no? No.
No.
In fact, it's a test to determine if the data are parametric. Okay. 2-sample t-test, homoscedastic? Yes.
Yes.
Heteroscedastic?
No.
No. Paired t-test?
Yes.
No.
No.
Remember, it can't be that because it's, okay, ANOVA. What is an ANOVA?
Analysis of variances.
What does that mean? What do you use it for? What's the purpose of it?
3 or more samples.
What about them?
Finding out if there is significant difference between them. And
Between the what?
the means.
The means. There we go. Okay. I want to keep all this straight. Okay, because everything has a different purpose. Yeah, so it's analysis of variance determines that there's a significant difference between means. Tukey, HSD, post hoc test.
Finding the difference, the specific difference of means between 2 different samples from the ANOVA test.
Or 2?
Or more.
3 or more.
3 or more.
Yeah. So you're looking for, so this, if the ANOVA test shows that, if the ANOVA test shows that there is a significant difference, you are free and clear to navigate with a post hoc test. And you can use Tukey's HSD. When?
When the sample sizes are the same.
And the sample sizes are equal. It's a very powerful test, so if you can use it, use it. If you can't use it, you use the Tukey-Kramer. Okay. Because it allows for non-equal sample sizes. Still pretty good, but it's just not quite as sharp. It doesn't quite have the power of the honestly significant different test. But those are good. Okay, excellent. So this review this helped me. I feel better. Okay. Now let's get to this new thing. What is correlation? Correlation. And I'll talk a little bit about this. My turn to talk now. Okay? And there's all sorts of different definitions to what correlation is. And we all know what correlation is because without a doubt when it comes to statistics, this is the most misused, abused thing that's ever done is correlation. Okay. What it is, all correlation is basically there's some sort of relationship between variables. Okay, so I have a group of variables here and a group of variables there. So is this parametric data? We're looking for a correlation between two data sets. Of course it's not it's not parametric data because we're looking for a connection between them. Okay. And oftentimes it's a measure of the relationship between 2 variables I can quantify. We oftentimes, not always, and I'll get into this a little bit later, oftentimes that relationship is linear. Okay. Another term for correlation is called covariation. As I vary, as this set of data varies, this set of data varies also in a similar way. Okay. There are lots and lots of covariate relationships in the world. We see them all the time. Some that probably every one of you in here has thought about maybe once or twice in your life. For example, fish length and body mass. right? If a fish gets longer, what happens to its body mass?
Gets higher.
We assume, right? We assume that there's a relationship. That if I have a 3-inch fish or a 3-foot fish, there's probably gonna be a difference in mass. If they're the same species, okay? Water temperature and dissolved oxygen. What's the relationship between water temperature and dissolved oxygen? My limnology people. As temperature goes up, what happens to dissolved oxygen?
Decreases.
And what?
Decreases.
It goes down, exactly. Okay. What happens to dissolved sugar? As temperature goes up, how about sugar? Okay, what happens to how much sugar you can dissolve in water? It goes up, right? What's up with that? How come I can dissolve more sugar in water, but I can't, warm water, but I can't dissolve more oxygen in water?
The sugar is denser?
Because you can't dissolve oxygen.
Because dissolved oxygen is not dissolved. You've been lied to your entire life. I hope you're happy. What we call dissolved oxygen is not dissolved oxygen, it's suspended oxygen. The oxygen does not dissolve in water. Well, be darned. That's a side note. Okay. Suspended sediment concentration. The amount of suspended material in the water and how deep and how much light goes into, how far the light can penetrate into the bottom. They're doing a measurement here called the Secchi disk measurement here. It tells you, you put a disc down to see how far down you can see the disc. As there's more suspended sediment, what happens to Secchi, the distance you can see in the water?
Decreases.
It decreases, okay? So as suspended sediment goes up, visibility goes down. Okay. As temperature goes up, dissolved oxygen goes down. As fish length goes up, fish mass goes up. These are all very relationships. Okay. The slope of a stream bed and the velocity of the stream. What's the relationship?
Slope increases, velocity increases?
Sure. Basically, you tip that stream, that water's going to come real fast. Okay, so great. So covariation can take on a couple different forms here. So first of all, don't assume what I've given you here have all been pretty good examples. Actually, they're not all pretty good examples of it. Don't assume that they're all a simple linear correlation. As one goes up, the other goes up. As one goes down, the other goes down. There's all sorts of different relationships. In fact, if I look at the length to mass of an insect, you would think that as the length gets bigger, the insect gets bigger. It does, but it doesn't follow a straight line. It goes up and it turns flat. Okay, so that's not a straight line. So there's lots of there, but sometimes there's relationships where something is low, the other thing is low, and as it goes up higher, then it goes up higher, and then it falls lower when the other thing goes even higher. For example, if I look at velocity of a stream versus discharge, as the amount of discharge is in the river, if the river is real low, and then velocity and discharge are low. As I increase discharge, velocity is getting faster and faster and faster until the river breaks out of its channels, and now the velocity slows. So again, the relationship, that's a true relationship, they're related, but it doesn't always follow a linear relationship. This is called a simple linear relationship, a nice one. But the good news is that's all, it's the most common, and that's all I'm going to work with, because these other relationships will hurt your head. They're often defined by second, third, and fourth order polynomial equations, and you don't need to be doing that. Okay. So what equation defines this simple linear correlation? What is the name? What is the equation? What is the equation of a simple linear equation? Every one of you better know.
Slope y equals mx plus b.
Remember it? Oh yeah, way back when. Y equals ms plus b, where m is the slope of the line, and b is where that line intercepts the y-axis. Okay, those two, that data right there defines any line, any linear relationship in the world. Y equals mx plus b. So far so good, okay? Another thing here, the x-axis is what we call the independent variable. Does anybody know the other name for x-axis, the proper name?
Horizontal?
No. It's called the abscissa versus
Okay.
the ordinate. Okay. Just wanted to, no one ever knows that anymore. Okay, so this is the independent variable on this axis. The y-axis then is known as the
Dependent.
dependent variable. Okay, xy dependent variable. okay, how do you determine which variable is which becomes the question. And many times it's pretty evident. Other times it depends. Of course, we know that the independent one is going to determine what the dependent one does. But it also depends on the research question you're asking. Okay. I know these sort of data, and I want to see if this sort of data is correlated. Okay, well then this is going to be your dependent, and this is your independent. So some examples. You decide here. Fish length and body mass. Which is which?
Length is the independent variable?
You're saying length is independent
Yeah.
and mass is dependent?
Yeah.
I would probably say that length is independent and mass is dependent. Oh wait, that's just what you said.
Yeah.
Yes, that's what we agree. Yeah, yeah. Okay, how about this one? Light penetration and suspended sediment.
Suspended sediment is independent.
Okay, you got a feel for this. That's dependent this time. Come on. And that's independent. Yeah, you get a feel for this. That's right. Okay, dissolved oxygen and temperature.
Temperature is independent.
Temperature would be independent, dissolved oxygen dependent. Stream slope and stream velocity.
Slope is independent.
Slope is the independent. Okay. Okay. So, what? Who gives a rodent's rear? Why do we care about this sort of stuff? Becomes the question. Okay. First of all, it tells you something about nature. We are scientists. Our job is trying to explain and understand the world around us. This is a kind of an interesting understanding. So basically, you know, and you as wildlife natural resource managers, you know, maybe if I start putting out more fescue, it seems to me that we might get more nesting or something like this, whatever. I could say fescue because
Palmer's not here.
Palmer's not here, yeah. So it also has predictive value. Okay, if you have a relationship and it's a strong relationship, and I know the independent variable is a certain amount, then I can predict what the dependent variable is. Okay. And along those lines, it can make your life a lot easier if you have a correlation. My example of that. Okay. Determining mass of your deer. In other words, how much does your deer weigh? How would you find out how much your deer weighs after you've harvested it? You have a scale. Okay, you carry one of the scales around with you all the time for measuring a deer?
Nope.
Nuh-uh. How else might you do it? Some of you've kind of done it here somewhere. Someone's had to have done it.
Overall size, length.
That's something more exact than overall size. No one's done chest girth?
Uh-uh.
Wow. Room full of you people. No, chest girth. Okay. There is a relationship of chest girth to the weight of your deer. Okay. So first of all, but you can. That's one way to do it. So you want to know the live weight of your deer, and you dress it in the field. And basically, the rule of thumb is the hanging weight times 1.68 gives you live weight. Okay, so that's the general rule of thumb. Is that linear? Is that a linear equation? As they say in Wisconsin, yeah, you betcha. That's so okay. What's that equation? It is 1.68x times 0 plus the y-intercept is 0 in this case. That's a linear regression. Okay. But anyway, so what a lot of people have done is basically measured chest girth for right behind the legs on a deer and weighed a whole bunch of them, a mess of deer, so that you could just carry a tape measure, and you can find them online, the numbers here, and you can take the girth and you can be really, really darn close to live weight, hanging weight, and meat weight. So there's all sorts of ways of dealing with that. So do look that one up. It's a good one to have in your tools. So there are three types of simple linear correlations. Actually, there's two, and then one is kind of cheesy. Okay. Three types of linear correlations. Okay. There's a positive correlation. As my independent variable increases, the dependent variable increases. That is a positive correlation. Everyone knows positive correlations, right? Okay. So in this case here, the slope is going to be greater than 0. And give me an example of a real, that I haven't already done. Let's make you think. Give me an example of a positive correlation in the real world that I haven't talked about. Two things that are correlated positively that we haven't mentioned.
Food consumption and body size?
Say what?
Food consumption and body size?
Could be. I'm not gonna argue with that. Yeah.
Mass production and squirrel abundance.
So the squirrel, so you're thinking that as mass production goes up, the squirrels go up too.
Yes.
Could be. Yeah. I mean, we don't have to test it. Yeah. Those are all nice. Those are good. The other correlation then, of course, is a negative correlation. Dependent variable decreases as the independent variable increases. That's negative. In this case here, therefore, the slope is going to be less than 0. It's a negative slope. Now, give me an example of one of those. Everybody else?
The
Wait
number
for Lily to answer it.
the number of squirrels decreases as the number of hawks increase.
That could be. That might be a good one. Or as you go up in altitude, temperature goes down. Average temperature goes down. As you go change in latitude, there's a change. The farther you go from the equator, the greater. Well, no, that doesn't work. That's actually positive. Okay, never mind. But yeah, so that works. Okay. Here's the third one. The third one is no correlation. So two things are not correlated at all. That there's none. One doesn't depend on the other. And when that happens, if two things aren't correlated, then the slope of the line approaches 0. Okay. Can you think of two things that are not correlated?
How many eggs fish lay and how many hamburgers people eat.
There's a good idea. Number of eggs laid by chickens per year versus how many hamburgers you eat.
Oh, well, I was
My favorite one that I use all the time is the time it takes a person, because I have the data for it, the time it takes a person to finish an exam and their final score on the exam. There's no correlation, because you got some people that whip right through that thing, you got others that take their time, you got some that are taking their time are actually praying for divine intervention. You got some that shoot through real quick, like, screw this, I'm out of here, so as a result, there's no correlation of time versus exams. So that's usually when I'm, I often have to produce graphs. You all got data, I gave you all. Well, where does that data come from? I make it up. And so that whenever I want data that is not correlated, I use those numbers and then just call them something different, That's where I steal from my own data. You'll have problems that are actually test data, because I'll say that's actually size of deer or something like that. So anyway, in other words, basically, the types of correlations are based on slope. Slopes that are greater than 0 are positive. Slopes that are less than 0 are negative. Slopes that are 0 are none. Yes, positive, negative versus no correlation whatsoever. So we did that. Okay, so now the question is, so you can see that, well, I'll get to that in a second. Okay, so basically there's different ways of measuring covariance. Your book, okay, that we're using here, he uses what's called the Spearman-Ranks sum. It's a measure. What this is a measure to tell you two things are correlated. How correlated are they? A lot, not so much, a lot, negative. Okay, so that's what these coefficients do. Spearman's is a good one, but in fact it's real easy to use, but we are not going to use it. We're going to use Pearson. Why? The reason we use Pearson is because it's in Excel, which makes it really easy. Spearman's is easy to do the math with. Excel is easy to do with no math, so that's why we use Excel. And we use the Pearson. Okay. So, and here's the equation for Pearson. It's equals Pearson, highlight your first array of data, and then you highlight the matching data with it, and you turn it in, you hit the button, and it gives you the Pearson coefficient value. Not a p-value, it's a Pearson coefficient value. I'll explain all this in a minute. So the full name of Pearson, Pearson Product Moment Correlation Coefficient. That's too long to say. Other names include the Pearson coefficient, Pearson's R, bivariate coefficient, and multiple R. The ones you're going to see, Pearson, Pearson's R, and multiple R. Remember multiple R, because it'll appear later in your life. Okay. How Pearson's R works. Okay. Pearson's R is always, 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 always. Remember that, because someone's going to try to trick you in the future about this. It's always a number between 1 and -1. Can't be anything more than that. Or I guess on the negative side, it can't be anything less than that. Okay. If the Pearson's value was 1, that means your two variables are perfectly and positively correlated. So in other words, if the independent variable is 1, and the dependent variable is 1, the independent variable is 2, the dependent variable is 2, 3, 3, all up the line, that would have a Pearson's value of 1. -1, the two variables are perfectly and negatively uncorrelated. 5, or 5, -5, 6, -6, 7, -7. You have a -1. If the values are completely uncorrelated whatsoever, perfectly uncorrelated, there's no correlation between them, Pearson is 0. Okay, so it's just kind of nice. Okay. Now keep in mind, in the real world, you never hit a perfect 1. You never hit a perfect -1, and you're never going to hit a perfect 0. It just doesn't happen. Okay. Why? Because there's variance in the data. So in other words, if I have a correlation coefficient of 0.95, is that a significant correlation? We don't know. It depends. Okay. If I have one of 0.5, is that significant? We don't know. It's going to depend on the power of your test. So somewhere in there, there's some significance. So somewhere in there, we've got another test coming up to count for correlation significance. Here's another value you want to see. I want to mention this sometimes. It's called R square, which is basically the square of Pearson. Okay. And what this is because of variance, what it is, this looks at the data, by taking R square, it's a way of looking at the data set. Well, I've got some variation in these data set. I've got some variation in this data set. How much of that variation between sets is due to each other? And so this is called a coefficient of determination. You'll see it sometimes. I'm not going to be using it in this class, but all it is, so for example, if you had a Pearson coefficient on R value of 0.8, your R squared would be 0.64. Okay. So that means basically 64% of that variation is from these two on each other. So, and not just garbage variation. So, to measure the proportion of the variance that's shared between the two variables. What are they causing? Yeah, I got variance here, but I got the same variance over here. So that more of that that's the same, the more the two are correlated. Okay, so now to get down to the brass tacks, I'm going to show you how to do this in Excel. Okay, so how do you calculate that? Okay, so this is the carapace length, again, remember that, and mass of crawfish. So carapace length and mass. In your head, how would they be correlated? If so, how so?
Positively.
It would be correlated, we would think a positive correlation. Okay, just like the fish length and fish mass. Okay. So here, let's say I took, this looks like 30 crawfish here. Yeah, that's what I said, 30. Here's their length, and here's their mass. Okay. So basically what you do is, so I've got your data on your sheet. And you would probably do the same thing. Your independent variable, you put in the first column. Your dependent variable in the second column, set it up there right at the top. And that's the only thing you got on the sheet. Stick it in A and B, right? Now I need a place for my answers to appear. Let's do that over in D. Okay. So I'm going to put my answer, the Pearson's, I'm going to have it calculated and put it in D2. Now, little side note here, you notice that I always put headers on everything. Okay, this is really kind of important because, again, just like before I talked about, you work real hard, you finally find that there is a significant difference, and then you ask yourself, what the hell did I just do? This is a significant difference of what? So assume that the next person to see your data is really stupid, and it's gonna be you, okay? So always, it's okay to label everything to death, is all I'm just saying here. So I know that I'm gonna drop Pearson's R right there, okay? So here's what I would write here. Remember, this is what I told you before, equals Pearson, highlight one array, highlight the next array. And that's where it's gonna get a little difference there. Okay. First of all, this is not case sensitive, by the way. You don't have to capitalize Pearson. You capitalize every other letter if you like, put them all lowercase, it doesn't matter. Okay. I just wrote it out capital so you can see it nice and clear. Array 1, array 2. Okay. And so for the example here, I could put in Pearson B2 to B31 is my first array, comma, C2 to C31 is my second array. Okay? I did that. I hit the button, and of course Pearson pops up with way too many decimal places, but that's all right. You're not showing me this on a graph or anything. It's just for here. So it's 0.50333022. Is that a significant relationship?
No.
The answer is not no.
Okay.
The answer is not yes.
We don't know.
We don't know. There's that word significant. You have done no, Pearson's, if you really think about it, Pearson's is sort of like descriptive statistics. Yeah, I'm describing the strength of this relationship, but you haven't done inferential yet. You haven't said, is that significant? So so don't jump to conclusions. Okay. Okay. What if you instead had typed Pearson and you put this array as the first one and this array as the second one? What would happen? Would matter. Not for Pearson. Later on, when I start talking about regressions, it will matter. But right here, it doesn't matter. The relationship's the same. Put those in either way. Dependent, array 1 versus array 2, independent versus dependent, doesn't matter. In this case, when you do that. Okay. Now, here's where it comes in here. How do we determine if that correlation is significant? That's what we want to do next. I want to be able to say, I've got this relationship, and it's significant. Therefore, I can use it to predict things. I can use to count one. I've got the chest girth and there to mass. It's significant. Great. I can make these I can carry around a tape measure from now on instead of having to lug a deer scale with me everywhere. Okay. So what are the hypotheses? The hypotheses go back to the slope. Remember, if we have a slope that's sufficiently close to 1, it's going to be significant. If it's sufficiently close to -1, it's going to be significant. If it's sufficiently close to 0, it's not going to be significant. So, the null hypothesis is then what we don't want. The null hypothesis is that slope is so close to 0 as to be not significant. And the alternative hypothesis is the slope is not equal to 0. And we're trying to blow this one out of the water so we can accept this one. This test is called a regression analysis. So testing of correlations is a regression analysis. Just like testing of the difference between two means is a t-test. And all those other tests. So here's the next one we're going to add to your list of things to do. Okay. Easily done with Excel. Thank you, Jesus. Because these used to be really hard. Okay? So, all you do is what you already did. Put your data into 2 paired columns. Okay? In fact, it's already set up. We already did it here. So this is fine. We can use the same data set. Okay? Okay? The one we used to figure Pearson's R. Okay? So you get to it just like you got to the ANOVA material. You click on data analysis, just like ANOVA. But now you don't hit one sample ANOVA. You scroll through the list until you get down to regression. Click on regression, and you're off to the races. So I'm sorry. Okay. So the first thing here, on this one, you define basically, it's going to ask you on there, it's going to say, okay, what is your Y range? And what it wants to know is, what are the dependent variables? Okay, well, okay, that's these guys. So you define that Y range first. This is where it matters here. It didn't matter with Pearson's, it does with this. You define the y range first, the dependent variables. Then you define the x range. Okay, and so that's good. If they don't match up, you have to have the same number of each. If you don't, you can't have a correlation, and you'll, of course, go into madness. So make sure they've got to be, they have to be paired data. Okay, and then you get you put somewhere, say, drop my output here, and what's it going to look like? It's going to look somewhat familiar to you. It looks like this. Okay, so it kind of looks, because it's looky there, it produces an ANOVA table. We don't care. It produces all this stuff. Most of this stuff, you don't care. It's wonderful. You just don't care. What you do, and with ANOVA you did care, because you had to use these numbers in your post hocs. You don't need them here. Okay? So what is important on this table? First of all, the very first number, multiple R. I told you what that means. That's Pearson. So remember when you calculated Pearson first? You didn't have to do that. This will give you, hopefully that'll be the very same number. Okay, there it is, 0.503320, yeah, so it's the same number. So that's important. Is this relationship significant that I just did? Looking at this table, would you say yes or no? You say yes, I'm impressed you can see it. If you say I don't know, that's a good answer.
I don't know.
I don't know, okay. Okay, so, okay, R squared, that's the coefficient of determination. What this is telling us, yeah, they're both variable, but 25% of that variable, one is causing on the other. Okay. That's great, wonderful. That's that R squared value. You don't really care. Okay. Then here it is, p-value down here under x variable 1, right there, p-value. This is the probability that the null hypothesis is correct. This is what we're trying to. We want this nice and small. How small do we want it?
Less than 0.05.
Smaller than 0.05. Look what we got here. Is this relationship, this comes as a shock to you. Do you realize that this means that the relationship between the carapace length of a crawfish and its mass are significantly correlated? Well, no kidding, right? Okay. So, and it appears in two places. Okay. Two other valuables things that are okay. So in other words, this has, and I realize I didn't show it on here, and this is kind of important, so I want to make sure I show you this. Okay. So what this is saying is this relationship is significant, is it not? Okay. And so it's a linear relationship. What is the equation of this line? And your answer should be, I have absolutely no clue, right? Yes, you do. The equation of this line is y equals 1.48x plus 30.53. They're right here. Okay, that's the slope of the line. That's the y-intercept. I realize I hadn't pointed those out to you. There it is. Solves everything. Okay. So now, I just found a crayfish that's got a carapace length of 43 millimeters. Or what am I using? Well, whatever. I know the length of the carapace. I can estimate its mass. So without even having to, I don't need that. My scale broke. I don't need it anymore. Okay. So predictions based on regression analysis. If two data sets are significantly correlated, okay, you can use a data point, a datum, from one of those sets to estimate the other data in the other set. If I've got carapace length, I can estimate mass. I could also estimate carapace length from mass, too. I just changed my equation, make it negatives. Okay. So if we know crawfish length, we can estimate its mass, because these are linear relationships. What is the equation of the line? Y equals mx plus b. So if we have the y-intercept and the slope, we can estimate for any y, any x. And you do have them. I guess I did show it to you. I forgot to put this slide in. Okay. So we know the relationship is significant. And we look at these coefficients here. The intercept coefficient is the intercept. And the variable 1 coefficient is the slope. B, and this is M. So you're good to go. There's the equation that we talked about before. I wrote up over here already. Okay. All right. We all good on that so far? Good, wonderful, hopefully. All that. So now, graphing these. There are rules to graphing correlations. Okay. Okay, if you're going to use a different technique, so far, all of our graphs have been using bar graphs so far. I don't think we even used a line graph or anything. When would you use a line graph? Do you remember? Could any of your data have used a line graph? Actually not. Okay. So a line graph, you only use a line graph so basically, okay, so for example, in your data, you graphed red oaks and white oaks. Could you have graphed white oaks and red oaks? Would have made no difference, right? Okay. Then that doesn't need a line graph. The order is important. Like temperature all over the day. You can't go 1 o'clock, 2 o'clock, 6 a.m., 4 o'clock, whatever. It's important. That requires a line graph. Months, altitude, whatever else. That's when you use a line graph. Okay? The data that we've been doing in here, they're basically independent data sets, so we can do that. Scatter plot is what you use for regressions, correlations. Okay? So you'll see the feature on there. So this is carapace length, and each data point is put in as a dot on there. And you could sort of, those are the data we've been using, and you can see, yeah, it looks like there's variance. We know that, but about 20-some% of that variance is due to each other, and as a result, I can sort of see the line. Okay. So the abscissa, or the x-axis, that's the independent variable. The ordinate, the y-axis, is always the dependent variable. Okay. Never mix those up. So if you look at a graph immediately, you know what you have declared as a dependent versus an independent variable. Okay. You can't, think, well, that would look better this way. No. This is not time for artistic expression. You've got to do it this way. Okay. Okay. What about graphing that nice line over top of it to show that? Okay. In Excel, that's called a trend line. All you have to do to get that is you click on your graph and it says trend line? Yeah! And it'll throw it in the equation right in there and put this beautiful line in your graph. Using it, this is where a lot of people make a mistake. If you're using that line, you are saying something very important. So sometimes you use it, sometimes you don't. Okay? If your analysis indicates significance, in other words, if your calculated p-value for the regression was less than 0.05, by all means put the line in. Because what that is you are signaling the reader, this is significant. Okay. If the regression analysis does not indicate significance, if that p-value is greater than 0.05, you do not put the line in. If you do, they come and get you. Okay? You don't want this to happen. Okay? So it's a bad thing. If you look around at the posters that have been put up on the walls, you'll see this mistake more than once. And I go by them every day and just get, it's another one of my I have a menagerie of pet peeves, and that's one of them right there. That somebody stuck a regression line and the Pearson's R coefficient, remember we went to close to 1 or -1, their Pearson's R coefficient was 0.0003. That's about as zero as you can get. So anyway, so that's one of, so when you draw, so if in the future you say you happen to be drawing graphs, which I think some of you may well be in the very near future with correlations on them, remember, don't put that line unless you've got every right in the world to put it. And if you have every right in the world to put it, put the line. Okay. So again, lots of trouble with correlations. Correlations are wonderful, wonderful, wonderful things. And they give us all kinds of insights. But they are as dangerous as heck. Okay? They're easily misinterpreted. Okay? First problem with correlations is if your sample size is too small. Okay? So I got 3 data points here. if I look at these three data points, by themselves, they look like a very strong positive correlation. In fact, it probably has a pretty strong Pearson's coefficient value. If I do the regression analysis, it's probably not going to be significant because regression analysis does take sample size in mind. You know, if you want a perfect regression, get 2 points. It defines any line, right? So, but it tells you nothing. So you know, if I sample 3 times and these are my regressions, that's fine. But the smaller the sample, the more likely you'll see a regression. But then you double the sample size and you see this. Okay, so this happens to be, these were my next 3 points. And I've lost my regression. I've lost my significance. The other thing too about this is, does everybody know what an outlier is? What is an outlier?
Oddball.
What?
A point that like doesn't represent the
It's,
same
it's
kind
something, yeah, so you collected all these data and you've got them, and you got one that's out there where the buses don't go. That's an outlier. Okay. In a regression, those guys tend to drive the correlation. So an outlier, of course, is a single unusual observation, and one point can drive the correlation. So here's an example here. So I got these points right here. They're showing me basically a negative correlation, all looking really good, and then I get this. Okay. That would have just turned this in the equation to a positive correlation. Okay. So the outliers, you got to watch for outliers. They can, so like, yeah, I'm getting a correlation here, but is it because of this data point? You know, I took all these data, and then I went and got drunk and took this one. You know, and so it could be a problem. Okay. The other thing is the effect size might be too small and missed. Okay. Do these look like there's a positive correlation there? Yes and no. That's pretty close to 0, that slope. But, so there may be an effect. You may be right. This may be a positive correlation. It may be significant. But because it's so light, you can't really see it. Okay. And the other thing too is, remember out there in the world, if you think the whole world is linear, it's not. This is a significant correlation, but it's curvilinear. It's not linear. Okay, so those things do exist in the world. So there may be a relationship, but you might miss it.
In the case of like an outlier, if that were to happen in our data, is there a way to like take out outliers, or would that create a bias?
Well, yes, all the things you say.
Okay.
What I would do is I would present it, actually your paper just got longer. I present both graphs
Okay.
and say this is what I got. However, a lot of think this is drawn by the outlier. You're talking to your readers, you know, so if I take that out, this is it. So is it justifiable to take it out? Well, let's talk about that point. So yeah, so that actually sometimes it's kind of cool to get an outlier because you can do that sort of stuff and make your paper longer. So, and here, without a doubt, is the biggest misinterpretation. Okay? Okay. Correlation does not equal causation. This happens all the time. In fact, it's so ingrained in our heads, we hear it all the time. Okay. Things like, so this is a good example probably, so that people that get into med school tend to read a lot of books. So let's say you wanted to go to med school. What would you think you should be doing?
Reading a lot of
You
books.
think you should be reading books. There's no evidence of that. Okay, so we hear it all the time that with that schools that have band programs have a higher GPA. So hey, we got to get a band program. Those are correlative data, but is there a cause and effect? Okay, these are what are called spurious relationships. Just because two things happen to be related to each other doesn't mean that there is a cause and effect. Okay. The two variables one appears to be causing the other, but it's not. Okay. Okay. Generally, what's usually happening is those two variables are actually correlated to something else that you're not even looking at. Okay. It's that third variable that's causing that this is correlated to that, and this is correlated to that third variable, but they've got nothing to do with each other whatsoever. Okay. And so while correlations can suggest a lot, okay, but really the main thing they're doing is, I'm seeing this relationship, it is significant. Okay. Is there a cause and effect? Okay. So when, in my early youth, all of a sudden the government started saying that smoking causes cancer. What did the tobacco companies say, do you know? Said there's no evidence of that. The tobacco companies were right. There was no evidence. Okay? But the more people smoke, the more likely they are to get cancer. That's a correlation. Okay? It wasn't until they actually showed lung cells mutating in the presence of TARs that you have the correlation. So really they were right. Okay? But you have a correlation doesn't mean cause and effect. So until you could show it. So of course it did cause it. Smoking was causing cancer, but in terms of being shown with scientific backing, until you can actually show that it happening, it really doesn't count. Here's the example. I used this out loud in class before this example. Talk about it again. Okay. Sales of milk in the United States and violent crime in the United States. Okay. This is the graph. Okay. If you look at comparison of the annual sale of milk in billions of pounds, some years you have a lot, some years you have a little, okay? Versus the number of violent crimes per 100,000 people, these are highly correlated. The more milk we sell, look at the p-value, 0.008. That's highly correlated. We're trying to hit a 0.05. Clearly, milk is causing us to attack each other. Shows it right there. We've got to stop drinking and selling milk. It's a completely spiritualist correlation. It has nothing to do with each other. One more thing I wanted to talk about, and that's just using, I'm going to go back to I guess this picture here. Okay, let's use this one here. One other thing, whenever you're drawing a graph, a correlation, you see that basically here, notice that my line starts with my first data point and ends with the last data point. That line should never go beyond those data points. That's another mistake. It's overplaying. So if you're, let's say, we want to know how much, we know this is a spiritualist correlation, but we know it's a good one. Okay, so we know. So let's say next year we're on schedule to sell 50 billion pounds of milk next year. What can I expect the violent crimes to be? Okay, I could basically use this, as dumb as it is, just use it as empirical data and kind of guess. What if next year we were going to sell 56 million pounds of milk? Could I use this graph? And the answer is no, because you're pressing your data. You've never sampled out at that distance. You can only, your correlation is only as good as your greatest and less value here. So if you find yourself drawing a graph and you've got lots of empty space with this line going down, I will nail you for that. Squeeze your graph and change the size of the axes so they end where your first data point starts. You can keep it a little bit just to keep it nice and clean, and where your last data point starts. So don't overplay your relationship. Mm-hmm.
Do you know, if there even is one, what the third variable between those two would be?
Yeah, it's year. Okay. Sales of milk have been going up. Guess what? So has violent crime over the last 20-some years. Yeah, that's all it is. It's just, the fact is the population's getting more violent and it likes its milk. So, more people, so probably it's overpopulation for counting for both of them. But that's all speculation. I didn't run the correlation.